So let's consider this other question on Fourier series defined in several subintervals. We have already solved the very first question in the first video, and I will post the link to that particular video on the description of this video. So do well to watch them up for proper understanding. So let's consider this other question. Still says write the Fourier series of the function f of x equals, we have 0 for minus pi to 0, and of course pi x all over 4 for 0 to pi. So first thing first, let's state our Fourier series. The Fourier series of a function f of x is given as a naught all over 2 plus summation from n equal to 1 down to infinity of an cos nx plus bn sin nx. This is our Fourier series formula, where a naught, an and bn are the Fourier constants. So let's start by solving for a naught. So I said when the function is defined in different subintervals and you're required to find the Fourier series, all you need to do is find the Fourier constants of each of these functions at their different subintervals, then add them all up together. In this case now, I need to find a naught. All I need to do is consider, of course, a naught is 1 all over pi integral. Now the first limit or the first subinterval, the very first subinterval is from minus pi towards 0. So we define that from minus pi to 0. That is now the interval of the first function f of x1 times the x. Then you add this with what? The same Fourier constant in the second interval. So this is 1 over pi integral. Second interval is from 0 to what? Pi. So you have from 0 to pi. The function at this point is f of x2, which is the second function times the x. It's as simple as this. So a naught is equal to 1 all over pi integral from minus pi to 0. F of x1 is the first function, and the first function in this case is 0. Okay, so this means 0 times the x plus 1 all over pi integral from 0 to pi f of x2 in this case is pi x all over 4. So you have pi x all over 4 times dx, and from here you can have that a naught is equal to 0 times everything here automatically becomes 0. So I have 0 plus, here I have pi is a constant, all over 4 is a constant, pull them out, this becomes pi, of course pi times 1 here is pi all over, I have 4 here, 4 pi integral from 0 to pi of x times the x. So from here, of course, pi can cancel pi here. That means my a naught is actually, this is now 0, so this integral is off. This becomes 1 all over 4 integral from 0 to pi of x dx. So this is equal to 1 over 4. If I integrate x, I'm going to have x squared all over 2 from 0 to pi. I can pull out this 1 over 2 outside this integral sign, or outside this sign, sorry. This becomes now 1 all over 2 times 4 is 8, 1 over 8. So I'm left with x squared. My limit is from 0 to pi. Alright, so at this juncture, you attain the limit. A naught is equal to 1 all over 8. Remember, upper limit comes first. So you have x squared there, and the upper limit is pi. This becomes pi squared minus lower limit is 0. This becomes 0 squared. So this is equal to pi squared minus 0 squared remains pi squared times 1 over 8. You have pi squared all over 8. So a naught is simply pi squared divided by 8. Having found a naught, next thing now is to find an. So let's continue that from here. So to find an, also an is equal to, you have 1 all over pi integral the very first word interval from minus pi to 0. So we have from minus pi to 0. This means now the very first function f of x1 times cos nx multiplied by the x plus 1 all over pi integral of the second interval now from 0 to pi. So you have from 0 to pi. This is now of the second function f of x2 cos nx times the x. You have this. So you put in the values of the function. An is equal to 1 all over pi integral from minus pi to 0. F of x1 is the first function, which is 0. So this is now 0 times cos nx dx plus 1 all over pi integral from 0 to pi of f of x2, and f of x2 here is pi x over 4. So you have pi x all over 4 times cos nx dx. So just like in the previous as earlier solved, 0 multiply everything here becomes 0. This means that an is equal to 0 plus, again, pi over 4 is a constant, pull them out. So pi times 1 gives us pi, all over 4 times pi here gives us 4 pi integral from 0 to pi of x cos nx times dx. So this means that an is actually, of course, 0 is off, pi goes into pi here, I'm left with 1 over 4, 1 all over 4 integral from 0 to pi x cos nx multiplied by the x. So once again, this is a product of two functions under an integral. So which means we are going to be employing the principle of integration by parts, which is the product integration to carry out this integration. And what is the principle? Integral of u dv is equal to uv minus integral of v du. So I said always let u be the given function and let dv remain the what? Fourier function under the integral sign. So u is equal to the given function, in this case is x, because it was crafted from where? Pi x all over 4. That is the function given to us. So u is equal to x, and dv always remain the Fourier function under the integral, in this case cos nx dx. So this is cos nx times dx. We've done all of this in the very first 3 videos we've done on Fourier series. Do well to watch them all up for proper understanding. Okay, so from the formula we need to find du and we need to find v. How do we find du? Simply by what? Differentiating u. If u is equal to x, then du is equal to what? dx. Now how did I get this? If u is equal to x, it means I can find du all over dx to be equal to what? 1. If I differentiate u with respect to x, I'm simply going to have what? 1. Now this is same as saying 1 divided by 1, so I can easily cross multiply. The x multiplies 1, du multiplies 1, so du times 1 remains du equals the x times 1 remains the x. So you simply have this. It's as simple as this. So du is equal to the x. And to find v is simply what? By integrating the v, which means you have to integrate this function here, cos nx times the x. And I've said to integrate a trigonometric function, okay, cos nx dx, to integrate a trigonometric function, first of all, you differentiate the angle. The angle there is nx. If I differentiate nx with respect to x, I will simply have what? N. Use this derivative to divide the integral of the three functions. If I integrate cos, I will simply have sine. Then pull back your angle and x. It's as simple as this. So the integral of cos nx dx is simply sine nx all over n. So this is simply sine nx all over n. All right, so let's plug in the values now. So we are actually carrying out this integral without the limit. Okay, but let's represent it now. Integral of, remember, what is u? U is x. You put it down, x. What is the v? The v is cos nx dx. So x cos nx dx. So which means that we are doing this integral first, x cos nx dx, without the limit 0 to pi and without this constant outside 1 all over 4. So that's what we're doing. Okay, until we effect this limit and this constant, then it turns to what? A n. So this is equal to, from the formula, u times v. What is u? U is x. You have x times, what is v? V is sine nx all over n. So you have times sine nx all over n minus integral of v times the u. What is v? Once more, v is sine nx all over n times du. What is du? Du remains the x. So you have times the x. Okay, so integral of x cos nx times the x is now equal to, this gives us x sine nx all over n. So I can factor out 1 over n here is a constant, to pull it out, it becomes minus 1 all over n integral of sine nx times the x. So this means I still have to integrate what? Sine nx further. Hence, integral of x cos nx dx is equal to, we have x sine nx all over n minus 1 all over n. So if I integrate sine nx, just like previously explained, to integrate a trig function, first of all, differentiate the angle. Angle there is nx. If I differentiate nx with respect to x, I will simply have n. Use this result to divide the integral of the trig function. If I integrate sine, I will simply have minus cos. Put it down, minus cos, then put down your angle and x. It's as simple as this. So integral of x cos nx dx is now equal to, we had x sine nx over n, x sine nx all over n. Now, mind you, this is minus 1 over n multiplied by minus cos nx over n. Minus times minus is plus, n times n here gives us n squared. So we have plus cos nx all over n all squared. At this point, it is simply a mere integral, but when we put in 1 over 4 multiplied by this limit 0 to pi, then it becomes what? An. Therefore, an is equal to, remember, 1 all over 4 integral from 0 to pi of x cos nx dx. So which means we are going to be multiplying this result by 1 over pi. So you have 1 all over pi multiplying all through by x sine nx all over n plus cos nx all over n squared. Now you put in your limits from 0 to pi. From 0 to pi. So an is now equal to 1 all over 4 into, let's put in all the limits, upper limits minus lower limits. So I will join them all together. Wherever you see x, put in the upper limit minus the lower limit. I have x here. Upper limit is pi minus 0. So I have upper limit minus lower limit pi minus 0. Sine, I have sine nx in place of x as well, upper limit. This becomes sine pi minus 0, upper limit minus lower limit times n all over n plus, I have here cos nx in place of x, upper limit pi minus lower limit 0. It becomes cos pi minus 0 all over n squared, all over n squared. Okay, let's proceed here. So an is now equal to pi minus 0 remains pi. So remember, 1 all over 4 into pi. Same thing, pi minus 0 here is pi, so you have sine pi n all over n plus cos pi minus 0 is pi, so this becomes cos pi n all over n squared. Now, I've said in front of a trig function, pi always appears as 180 degrees. Pi is equal to 180 degrees in front of a trig function. So this means that an is equal to 1 all over 4 into, this is pi sine, in place of pi n it becomes sine 180 n all over n plus, in place of cos here, cos pi here, this becomes cos 180 n all over n squared. So sine 180 is 0. Automatically, everything here becomes 0. Cos 180 is 1. So this becomes, this implies an is 0. Not forgetting 1 over 4 into 0 plus 1 all over n squared. So this becomes, of course, 0 plus 1 over n squared remains 1 over n squared times 1 over 4. This is 1 all over 4n squared. Hence, an is 1 over 4n squared. Let's put it down here. An equals 1 all over 4n all squared. Having found an, finally we find what? Bn, which is the last Fourier constant. So to find Bn is equal to same thing, 1 all over pi integral for the very first limit. First limit is from minus pi to 0. We have from minus pi to 0 of f of x1 multiplied by sine nx times dx plus 1 over pi integral. Second limit now from 0 to pi. So you have 0 to pi. This is of f of x2 sine nx times dx. So let's put in the values. Bn is equal to 1 all over pi integral minus pi to 0. F of x1 is the first function, which is 0. So you have 0 times sine nx times dx plus 1 over pi integral from 0 to pi f of x2 is pi x over 4. So we have pi x all over 4 times sine nx multiplied by dx. Again, bn is equal to 0 times everything here automatically becomes 0. So we have 0 plus. So from here, pi over 4 is constant. Factor them out. Pi times 1 here is pi. 4 times pi here becomes 4 pi. So this is pi all over 4 pi. Integral from 0 to pi. We are now left with x sine nx multiplied by dx. So which means that bn is equal to, of course, 0 here is off. Pi goes into pi is off. So I have 1 over 4 there. Bn is simply 1 all over 4 integral from 0 to pi of x sine nx multiplied by dx. Again, this is a product integration, so we simply employ the principle of integration by parts, and so we can just do this all together since we already explained the principle earlier in this video. So let's just solve it together. This will be equal to 1 all over 4 into, remember the formula, it becomes uv minus integral of v du, putting the limit from 0 to pi. You have this. So what is u again? U is the given function. In this case, u is x, and the v remains the Fourier function under the integral sign, which is what? Sine nx times the x. How do we find the u from the formula? The u is by differentiating x, that gives us what? The x. And v is simply by what? Integrating the v, which is integrating sine nx dx, and this is equal to, if I integrate sine nx dx, I've already done this earlier. Integrate sine, we have cos nx minus cos, please, minus cos nx all over n. Okay, so let's plug into the formula. Bn is now equal to 1 all over 4. Okay, formula says u times v, and u is x, so this is x times v is minus cos nx all over n minus integral of v du. V once more is minus cos nx all over n times du. Du simply gave us the x, so multiply by the x. Forgive me guys, I'm racing too much, the video is getting too long. So this is from the limit is from 0 to pi, that becomes the limit. All right, so bn is equal to 1 all over 4 into, rearranging this now, I have minus x cos nx all over n. Okay, minus times minus here is plus, then I can factor out 1 over n. This is now plus 1 all over n integral of cos nx times the x, putting your limit from 0 to pi. So this means I still have to what? Integrate this function cos nx dx. So bn is equal to 1 all over 4 into minus x cos nx all over n, okay, plus 1 all over n. If I integrate cos nx dx, if I integrate cos, I'm going to have sine nx all over, divided by the number n. It's as simple as this. All right, okay, then you put in your limit from 0 to pi. So let's work on that integral over here. So bn is equal to 1 all over 4 into x minus x cos nx over n minus x cos nx all over n. Now observe here, sine nx multiplied by 1 remains sine nx all over n times n here remains n squared. So this is plus sine nx all over n squared from 0 to pi. So you can append the limits. So I will do them all together. So bn is equal to 1 all over 4. Wherever I see x, I will put in my upper limit minus my lower limit. So I have minus x here, put down a minus sign, there is x here, upper limit is pi, minus lower limit is 0, cos, I have x here, cos nx, in place of x, upper limit is pi, minus lower limit is 0 times n, all over n, plus, this is sine nx, so in place of x, upper limit is pi, minus lower limit is 0 times n all over n all squared. So you have this. Let's continue here. So this is equal to 1 all over 4 into pi minus 0 remains pi. So this becomes minus pi cos pi minus 0 also remains pi. So this is cos pi n all over n plus sine pi minus 0 remains pi. So you have sine pi n all over n all squared. And I said in front of a trigonometric function, pi always appears as 180 degrees. So this simply means that bn is equal to 1 all over 4 into minus pi cos 180n all over n plus sine 180n all over n squared. And sine 180 is 0, whereas cos 180 is 1. So sine 180 is 0, automatically everything here becomes 0. So Bn is equal to 1 all over 4 into cos 180 is 1. 1 times minus pi remains minus pi all over n. Okay, minus pi all over n. Alright, so evaluating this now, this implies that Bn is equal to minus pi times 1 is minus pi all over 4 times n gives us 4n. Okay, so Bn is actually minus pi all over 4n. So we have our Fourier constants. Let's now attempt to write the Fourier series. Once again, we find when n is equal to 1, let's find a1 and b1. So a1, this means now wherever you see n, put in the value as 1. So an becomes a1, and an gave us 1 all over 4n squared. N now is 1. This becomes 1 all over 4 into 1 squared, and 1 squared remains 1. This is now 1 all over 4, because 4 times 1 is 4. This implies that a1 is simply 1 all over 4. Therefore, b1 will now be equal to, wherever you see n, putting the value as what? 1. So in place of bn, we'll have b1. This is equal to minus pi over 4n. So you have minus pi over 4n. N now is 1, so it becomes over 4 times 1. And this is simply minus pi all over 4. So this simply implies that bn is actually minus pi divided by 4. That's for bn. When n is 2, sorry, this is b1. Okay. When n is 2, when n equals to, we find now a2, which means wherever you see n, put in the value as 2. So an is equal to, once again, it is 1 all over 4n squared, but n now is 2, so this is 1 over 4 into 2 squared. This becomes 1 all over 4 times 2 squared is 4, which is simply 1 all over 16. So this means that a2, this implies that a2 is equal to 1 divided by 16. Let's find b2. b2 is equal to, same thing, bn is what? Minus pi over 4n. So this is simply minus pi all over 4, n is 2. So you have minus pi all over 4 times 2 is 8. This simply implies that b2 is actually minus pi all over 8. I think we can end it at 3. It's a series that runs from 1 to infinity, so you can stop at any point. So let's stop at 3. When n is equal to 3, then a3 is equal to, an is simply 1 over 4n squared. So you have 1 all over 4. N now is 3, so this becomes 3 squared. Okay, 3 squared. This is equal to 1 all over 4 times 3 squared is 9. So you have 1 divided by 4 times 9 gives us 36. So you have 1 all over 36. So this simply implies that A3 is simply 1 divides 36. And similarly, B3 becomes, remember, minus pi over 4n, and n is 3. So you have this. This is actually minus pi all over 4 times 3 is 12. So this simply implies that B3 is actually minus pi all over 12. Let's write our series over here. So the Fourier series of these functions f of x is now equal to, remember, a naught from the formula, a naught all over 2, and a naught gave us pi squared over 8. So this becomes pi squared over 8 divided by 2. So simply multiplying 2 under here. Alright, plus now summation from n equals 1 to infinity of these constants an cos n as the x plus bn sin n as the x. Alright, so n starts from 1 and runs to infinity. Since you cannot approach infinity, that's why we stop at 3. You can do up to 4, or depending on how many the question is asking you to do. So let's start with the cosine series before going to the sine series. So for the first case, when n is equal to 1, we had a1 to be equal to 1 all over 4. Therefore, this is 1 all over 4 cos nx, and n now is 1. So 1 times x remains x. So this is simply 1 over 4 cos x. Plus, when n is equal to 2, we had a2 to be equal to 1 all over 16. So this is 1 all over 16 cos n now is 2, so it becomes cos 2x. Plus, we stop at 3. a3, when n is equal to 3, we had it to be 1 all over 36. So this is 1 all over 36 cos 3x plus. Okay, so let's stop there for the cosine series. Now we'll move to the sine series bn. So when n is equal to 1, we had b1 to be minus pi over 4. So this is simply minus pi all over 4 sine nx. But n is equal to 1, so it becomes sine x. Okay. Let's move to b2. When n is equal to 2, we had minus pi all over 8. So this is simply minus pi all over 8 sine 2x. Now n is equal to 2, so it becomes sine 2x. And we stop at 3. So b3 is minus pi all over 12. So minus pi all over 12 sine 3x. So the series continues like that without an end, because it runs to infinity. Okay, so let's rearrange. So the Fourier series of that function f of x is now equal to, so pi squared divided 8 times 2 becomes pi squared all over 16. We have pi squared all over 16 plus, okay, this can be written as cos x over 4. So you have cos x over 4 plus, this can be written as cos 2x over 16, cos 2x all over 16 plus, this can be written as cos 3x all over 36 minus, this can be written as sin x sin minus, this can be written as pi sin x all over 4 minus, again we can write this as pi sin 2x over 8 pi sin 2x all over 8 minus pi sin 3x over 12 sin 3x all over 12 plus, and the series continues like that. So this becomes the answer to the Fourier series of that given function. Alright guys, so that's it on the idea behind Fourier series defined in different subintervals. If you have any questions at all, do well to drop in the comment section.